In this video, we're going to focus on solving problems that involve calculating someone's resultant displacement. So let's work on this one. Karen walks 5 meters east and then 12 meters north. So let's draw a picture. So she travels 5 meters east and then 12 meters north. What is the magnitude and direction of Karen's resultant displacement? To draw the resultant displacement vector using the head-to-tail method, simply draw an arrow from where you started to where Karen ended. And so that's going to be the resultant displacement, which we can simply call d. The 5 meters, that's dx. dy is the 12 meters. You can think of it as the resultant displacement in the y direction. So to calculate the resultant displacement d, we could simply use the Pythagorean theorem. A squared plus b squared is equal to c squared, but c is going to be the square root of a squared plus b squared. So d is the square root of dx squared plus dy squared. So dx is 5, dy is 12. 5 times 5 is 25, and 12 squared is 144. 25 plus 144 is 169, and the square root of 169 is 13. So this is the magnitude of the resultant displacement. It's 13 meters. And so what we have here is the 5, 12, 13 triangle. Now let's calculate the direction of the resultant displacement. Typically, this is the angle usually measured from the positive x-axis, but you could describe it in many ways. The angle theta is going to be equal to the arctangent of the y component divided by the x component. That'll give us the reference angle in the triangle. So if we take the arctangent of 12 over 5, this is also called the inverse tangent, it'll give us the answer. By the way, make sure your calculator is in degree mode, because if it's in radian mode, you're going to get a different answer. So you should get 67.38 degrees as measured from the positive x-axis. Now, you can also describe it a different way. This is east, this is west, this is north, this is south. So we can also say that, I'm going to round it to 67.4, just to keep things simple. We can also say that the displacement vector is 67.4 degrees north of east. Now, if you find the complement of that angle, 90 minus 67.4, this part here is 22.6. So we can also say that it's 22.6 east of north. So those are some different ways in which we can describe the answer, but we can leave it like this. We could say it's 67.38 degrees relative to the positive, or counterclockwise to the positive x-axis, or 67.4 degrees north of east. Now let's try this example. Tim travels 30 feet west and then 40 feet north. So if you want to try this, feel free to pause the video and work on this example. I'd like to begin with a picture. So 30 feet west and then 40 feet north. So now let's draw the resultant displacement vector from the beginning to the end. So the horizontal displacement is 30 feet. The vertical displacement, dy, is 40 feet. So let's calculate the magnitude of the resultant displacement using the same formula. So it's going to be the square root of 30 squared plus 40 squared. 30 squared is 900. 40 squared, or 40 times 40, that's going to be 1600. 900 plus 1600 is 2500. Now 2500 is basically 25 times 100, so you could split it into two radicals. The square root of 25 is 5, and the square root of 100 is 10. So the square root of 2500 is 50. So the magnitude of the resultant displacement, it's 50 feet. Now we need to calculate the angle. Let's calculate the reference angle in that triangle. And then we'll make the appropriate adjustments. The reference angle, or the acute angle within the triangle, is going to be the same as we got before. Like, the process of calculating it is the same. It's going to be the y component over the x component using the inverse tan function. So it's going to be the arctangent of 40 divided by 30. So that's 53.1 degrees. Now let's get the angle as measured from the positive x-axis. So this angle here is 53.1 degrees. If we want to get the angle from the positive x-axis, it's going to be 180 and then minus 53.1 degrees. So it's 127 or 126.9 degrees counterclockwise from the positive x-axis. That's one way in which you could describe the direction of the resultant displacement. If you want to use this angle, you could say it's 53.1 degrees north of west. Keep in mind, this is west, north, east, south. So it's 53.1 degrees north of west. Now let's try this one. It's a little bit longer, but we'll work on it anyway. So John runs 190 meters east. Let's draw that. And then he travels 60 meters south. After that, he travels 40 meters west. And then he's going to travel 140 meters north. So the resultant displacement, if we draw it from where he started to where he ended, will be here. So it's going towards the first quadrant. But how can we find the magnitude of the resultant vector? What we need to do is get the net displacement in the x direction and the net displacement in the y direction. In the x direction, he traveled east by 190 meters, and he traveled west by 40 meters. If we combine those two, we get a net displacement of positive 150 in the x direction. Now what about his displacement in the y direction? Well, he traveled positive 140 meters north, negative 60 meters south. So 140 minus 60 is 80. So he went positive, a net of positive 80 meters north. So now we can redraw the picture. So the net horizontal displacement is 150 east, and the net vertical displacement is 80 meters north. So that's our resultant vector. And so d is going to be the square root of the dx squared, which is 150 squared, plus dy squared. So this is going to be the 8, 15, 17 triangle. Thus our answer should be 170. But we'll do the math anyway. 150 squared is 22,500. 80 squared is 6,400. Now let's go ahead and add the two numbers. So the sum of those two numbers is 28,900. And the square root of that, 170. So the magnitude of the resultant displacement vector is 170 meters. So that's the distance from where John started to where he ended. Now let's get the direction. So let's calculate the reference angle. It's going to be arctangent or inverse tangent of the y component, which is 80, divided by the x component, 150. So that's going to be approximately, let's use the approximate symbol, 28.1 degrees. Now we could say that's counterclockwise from the positive x-axis, or we could say 28.1 degrees north of east. Now this one is going to be a little bit harder because there's more complications to this problem. But let's begin. Susan walks 3 miles east. So let's draw that. And then she travels 4 miles at 30 degrees north of east. So this is north, this is east. Starting from east, we need to travel 30 degrees towards the north. So in this general direction is where the second vector is going to be. So it's 30 degrees above the horizontal, or above east. And she's going to travel 4 miles in this direction. So the resultant displacement, we could draw it from where she started to where she ended. So that's going to be that portion there. Now, in order to figure out the resultant displacement, what we need to do is break up the two vectors into x and y components. So let's call this D1, and this is going to be D2. So D1 is a horizontal vector. That means it has a horizontal component, but no vertical component. So D1x is 3 miles. The y component of D1 is 0. Now let's do the same thing for D2. We need to break it up into its x and y components. So this is D2. It has a magnitude of 4 miles. It has an x component. We'll call it D2x. And it has a y component, D2y. Now the angle here is 30 degrees. To calculate the horizontal component, it's going to be D2 times cosine theta, or in this case, cosine of 30. And D2 is 4, so it's going to be 4 cosine 30 degrees. D2y is going to be 4 sine 30. Sine 30 is 1/2, so half of 4 is 2. Cosine 30, that is 0.866 times 4, so that's going to be 3.464. So D2x is 3.464 miles, and D2y is 2. Now keep in mind, you can also represent D1 using I and j. You could say D1 is 3i plus 0j because there's no y component. I corresponds to x, j corresponds to y, z corresponds to k, or k corresponds to z. D2, we can write that as 3.4 64i plus 2j. When you start getting multiple vectors with angles, the math becomes easier when you write it like this. So now let's calculate the resultant displacement. The resultant displacement is the sum of these two vectors. It's d1 plus d2. And what we need to do is basically add the horizontal components and the vertical components together. So adding these two, we're going to get 6.464i, and then adding those two, we're just going to get plus 2j. So this is the displacement, the resultant displacement in component form. This is dx and this is dy. So now we could find the magnitude of the resultant displacement. It's going to be the square root of dx squared, which is 6.464 squared, plus dy squared, which is 2 squared. And that works out to be 6.766. And the unit is miles. So that's the magnitude of the resultant displacement. Now let's calculate the angle, the direction. So we have an x component of 6.464 and a y component of 2. So that is our resultant displacement. Now we need to find this angle, theta. So it's going to be arctangent, the y component, which is 2, divided by the x component, which is 6.464. And this is going to be north of east, whatever answer we get here. So the angle is approximately, let's do that again. It's approximately 17.2 degrees. So that's it for this problem. So the magnitude of the resultant displacement is 6.766 miles, and the direction is 17.2 degrees north of east, or counterclockwise from the positive x-axis. Now let's try another one, but this time with 3 vectors. So Kim, she runs west 200 meters, and then 300 meters at 20 degrees west of north. So let's see what that is. Here's north, here's west. So relative to north, she goes 20 degrees west from that. So that will be in this direction, with this being 20 degrees. And she travels 300 meters in that direction. And then she's going to go 400 meters at 40 degrees west of south. So here's south. We need to go west of south. So this would be 40 degrees west of south. And she's traveling 400 meters in that direction. So let's call this the first vector d1, the second one d2, the third one d3. And let's break it up into components. So d1 has an x component of 200, but because it's west, it's negative 200. It has no y component, nor no horizontal component, so it's 0j. Now, D2 has an x and a y component. So I'm going to redraw D2. D2 is in this direction. If this is 20 degrees, the complement of that is 70. So it's 70 degrees with respect to the x-axis. So now what we need to do is find out D2x and D2y. We know D2 is 300. Now, when using the sine and cosine functions to get the x and y components, you need to make sure you pick the right angle, because the formula changes depending on which angle you use. So if you look at these two angles, the 20-degree angle and the 70-degree angle, which one do you want to use? The 20-degree angle is between the vector and the y-axis. The 70-degree angle is between the vector and the x-axis. I like to choose the angle between the vector and the x-axis, because when you do that, it's easy to remember the formula. The x component is going to be the vector times cosine theta. The y component is always going to be the vector times sine theta. This works if you choose the angle between the x-axis and the vector. If you choose the angle between the x-axis, between the vector and the y-axis, you need to reverse sine and cosine in order for that to work. So just keep that in mind. Therefore, d2y is going to be d2, which is 300, times sine of 70 degrees. d2x is going to be d2, which is 300, times cosine 70. So let's get the x component first. 300 cosine 70, that's 102.6. Now, keep in mind, we need to add positive and negative signs. d2x is going west, so it's going to be negative. d2y is going up or north, so it's positive. So we need to introduce a negative sign here. So this is going to be negative 102.6. 300 sine 70, that's going to be positive. Let me round this even better. This is 102.61. And this other one is going to be 281.91, just to get a more accurate answer. Now let's focus on the third vector. So it's moving towards quadrant 3. The angle between the vector and the y-axis is 40. So the angle between the vector and the x-axis is 50. Those two complementary angles have to add up to 90. So now let's get d3x and d3y. Now d3x is going towards the left, so it's negative. d3y is going down, so both of these values must be negative. d3x is going to be d3, which is, it has a magnitude of 400, times cosine of 50 degrees. That's the angle between the x-axis and the vector. And then d3y, that's going to be 400 sine 50. Now, whenever you use a reference angle, which is an acute angle between 0 and 90, the angle inside the triangle, you need to adjust the signs. So if it's going to the left or if it's going down, it's negative. If it's going to the right or going up, it's positive. So now let's go ahead and plug this in. 400 cosine 50, that's 257.11. But we need to introduce the negative sign. So negative 257, actually 0.12 if we round it. Now 400 sine 50, this is going to be negative 306.42, and then j. So now the three vectors, we broke it down into components. So now we're going to add up all the components to get our resultant displacement. So let's begin by adding all of the x components. So we have negative 200 plus negative 102.61 plus negative 257.12. So that's going to be negative 559.73. And then we have 281.91 plus negative 306.42. So that's negative 24.51 j. So the x component is to the left, that's dx, and the y component is slightly down. So the resultant displacement will be in quadrant 3. I will find the reference angle. So the reference angle, we can put theta r for that. It's going to be arctangent, and it's the y component divided by the x component. For the reference angle, you don't need to worry about the negative signs, because we're going to adjust the answer based on what quadrant it's in. So you could just type in arctangent 24.51 over 559.73. And so this angle is going to be pretty small. It's 2.51 degrees. But that's this angle here. So we could say it's 2.51 degrees. And relative to west, we're heading south of west. So that's what it is. 2.51 degrees south of west. So that's the direction. And we need to calculate the displacement as well. I forgot to do that. That's going to be the square root of 559.73 squared plus 24.51 squared. Once you square it, the negative sign doesn't matter because all the numbers will become positive. Alright, so let's go ahead and get our final answer. So I got approximately 560.27, but we can round that to 560.3, and the unit is meters. So that's the magnitude of the resultant displacement. It's very close to this number because this number is significantly larger than the y component. So that's it for this video. Now you know how to calculate the resultant displacement for a variety of different problems.